Okay, good morning to everyone. It's the middle of the week already. See what happens when you get one day off and then the week goes by that much faster. Okay, we've got Jeff Swank back with us at the controls this morning. As I said, the master's back with us. Jeff has done a lot of the camera work on particularly the Math 10 when you go back and look at those tutorials and some of the 134. And I have several questions for you, Jeff, regarding music. One, that was Dire Straits, and the cut was?
Heavy Fuel.
Heavy Fuel. Tell us about Dire Straits.
Dire Straits. Mark Knopfler, great guitarist, songwriter, leader of Dire Straits. Got a lot of work with other notables like Chet Atkins, great guitar players.
Okay. That's the kind of thing that, see, comes on a day that Jeff's here. Now, the next question. Did you watch the Rolling Stones on the concert they did from Madison Square Garden?
No, I didn't.
What? You didn't?
I must have been asleep or something.
Not obviously motivated to... Well, this is not one of your favorite groups, of course, so...
Well, no, but...
You haven't had a chance to see that, huh? That was rather interesting. It was certainly in terms of the energy, the quality of the music, and the oldies but goodies they played was really neat. And it started out a little bit it just seemed a little bit strange to see Mick Jagger doing his thing. Well, but it was acceptable after a while, and it got darn good. I really enjoyed it.
To see Mick Jagger.
Well,
That's exactly.
okay, enough said. We're back to algebra, and I have a request, speaking of music, a request that came through from the homework. It's problem 69 on page 170. And I'm really pleased that this one was requested because it's something that I need to talk about and address. And there's the problem on the document cam. And of course the question is, how do you read a problem like this? So while that's still in the document
right.
cam, I'm going to write it so I can see it.
That's not right.
That's not last night.
That isn't last night.
No.
On the inequalities? Didn't we have inequalities last night, 1 through 70 on? Okay, let's come back off there. I thought we had 1 through...
It's page 159.
159.
On inequalities, is that a review problem? That's a review problem. I was looking at it as an inequality. I will go back and look at that. I'm still going to do that problem. Because I assume this was the inequality from the homework. Obviously it isn't. But I'm still going to write it down, and we're going to look at this for a moment because we need to talk about this. Then clearly I'm going to have to do another number 69. So this is a problem which I'd like to come back to briefly. The point is, on this problem, we have two statements. Now the question is, how do you read this kind of problem? What you say is the following. 2m plus 1 is greater than or equal to minus 3 and less than or equal to 4. It's a little bit like taking a compound sentence in English. You want to say, I went to dinner. I went to a show. So what do? You take the subject and combine those two and say, I went to dinner and a show. So this says first that minus 3 is less than or equal to 2m plus 1. Well, that is equivalent to this statement. 2m plus 1 is greater than or equal to minus 3. You must be able to take a statement and rewrite it with the different inequality. You're just switching it around. And it also says that 2m plus 1 is what? Less than or equal to 4. So that's like saying, okay, now I went to dinner, I went to a show. 2m plus 1 is greater than or equal to minus 3, and 2m plus 1 is less than or equal to 4. Well, now you put it together. 2m plus 1 is greater than or equal to minus 3, and less than or equal to 4. Now the question, you could come back and do each of these as separate statements, but how could you do this all at once? So the idea is you want to isolate the variable. So you would, in essence, subtract minus 1 from every single part of this expression. So you're going to have minus 3 minus 1 is minus 4, less than or equal to 2m, less than or equal to 3. Again, we want m by itself. So what can I now do to get m by itself? Divide every single part by 2. Do I have to worry about the direction of the inequality symbol?
No.
The answer is no, because I'm multiplying by 1/2. I remember we talked about a multiplication property for inequality. We talk about multiplying by a positive number, and the direction of the inequality does not change. Multiplying by 1/2 is the same as dividing by 2. So I'm talking about a multiplication in essence. So this gives us minus 2, less than or equal to m, less than or equal to 3/2. So m is a number in a closed interval. The closed interval that's involved here is open on the left side at minus 2, open on, that's closed on the left side. I was focusing on the less than symbol. It is closed on the left side and closed on the right side, meaning I want all the values in that interval. If I do the related number line for a solution, and I sometimes get the impression when I do these that 0 is in the center. Well, since the number line goes infinitely far in both directions, to say that it's centered in that way, probably inappropriate. But I'm going to come out here with a 1.5, so that's a point right here. I'm going to enclose that. I'm going to put a 1 here and a 2 here so that you can see I'm at 1.5. And then I'm going to come down here to a negative 2, and I'm going to enclose that with a full circle, and then everything in between is part of my solution. That type of notation is a very important problem if you were to go on in mathematics. Now, I don't know just how far you plan to carry on here, algebra and beyond, and I don't know where beyond is. But if you were to go into the pre-calc and calc sequence, this is language that's going to be used there very, very often. Any questions on what I did in the problem? That's a good test question. Now there's a question. Yes?
So both are actually
Both.
the closed -2.
All three.
Okay, all three.
Okay, we have these two and this. They are all different ways of providing the answer. And I want you to be able to do all three techniques. Good question. Other questions there? Okay, 69 on the set of problems that we did. So let me back up. That's 159. Number 69. Well, sure enough, it's the same thing. Different numbers, but the same basic problem. Let me see if I can get that. I'm trying to get that so I have plenty of light on it. I think we can do that now, Jeff. Okay, do you see the similarity? What we did before is what we do now. Same idea. A little more difficult with the 5/4 because I'll have to multiply by 4/5. But what's your first step as you eyeball that problem?
Add 1.
Add 1 to everything. So let me write that first. This is another 69. This is the correct one. So I have -7 less than or equal to 5/4 times r minus 1 less than or equal to -1. Now as we come back to the board, what we have to do is add 1 to everything. So that's going to give me a -6 here, less than or equal to 5/4 times r less than or equal to 0. Now that makes it pretty nice because you know the right side is going to be 0. If I multiply everything by 4/5, 4/5 times 0 is going to be 0. 4/5 times 5/4 is going to be 1. So the only thing that's of particular interest is right here. Multiplying by 4/5 is going to give me -24/5. That's less than or equal to r, which is less than or equal to 0. So I have something that's going from, well, it's all the values between -24/5, which is nearly what?
-5.
Nearly -5, just a little bit under it. And going to 0. So again, and there's nothing gained by doing the division here. There's your solution set, method 1. Here's your solution set. I guess this is method 2, method 1. And then what would you do down here on the number line? Well, you'd have your 0. That's a 16 arrow. You'd have your 0 here. You have 1, 2, 3, 4, 5. And so just before 5, I'm going to have another closed circle here, and everything in between, and that is an arrow going out that way. So this is at -4 and 4/5 if I do it as a mixed number, and this, of course, is at 0. And that is the sickest looking -4 and 4/5 I've ever seen. So let me try doing this, -4.8. Okay, and that makes it a little bit more readable. Question?
So the comma means anything in between.
Everything in between.
All the...
Yeah, all the values, all the possible values. That's decimals, fractions, counting numbers. Any point between these 2 points in the number, any point between these 2 points in the number line will be a solution. So this one right here is going to be saying the same thing, including the endpoints. Now, if this was strict inequality, no equal sign, what would I do differently here?
Not including the parentheses.
Parentheses instead of square brackets, and what would I do here?
No.
Open circle rather than a closed circle. We got it?
Yeah.
Very important problem, and I did not give it enough time when I was doing this. Yes?
What if you tried to get rid of the fractions first?
Okay, getting rid of the fractions first, up here. Go through and multiply by 4 all at once. It'll work.
No.
Numbers get larger, not anything gained. I'm a little more inclined to isolate first, unless I had other fractions. Now, if I had a 2 here and an 8 out here, then I'd find an LCD. But if it's just a single fraction in front of the variable, I'm more inclined to isolate the variable, then multiply by the reciprocal to get the coefficient of 1. If you feel better about getting rid of that denominator first, it's okay. The numbers get a little bit larger, but you'll get the same answer. Yes?
When we graph on the number line, can we use parentheses and brackets instead of closed circles, open circles?
I know the text does it that way. I don't particularly object to it. It's just I find that people are sloppy enough you can't sometimes tell the difference between a bracket and a parentheses. And so by using an open circle, closed circle, it seems to communicate better, and I don't have to play a guessing game. And if I play a guessing game, I do not give you the benefit of the doubt. You're out. Okay, in baseball, the tie goes to the runner. In this class, the tie goes to me. Okay, any other question there? Any other questions in the homework? Yes?
Okay, can you explain one more time how you use the brackets and the parentheses?
Okay, the brackets and the parentheses. When I have less than or equal here, it says R could equal -4.8. This bracket tells me that I could have equality. If this was just a less than symbol here, then I would use a parentheses because -4.8 is not a solution. It goes up to but not including the endpoint. So all that the bracket does is say the endpoint is included. In the same way, filling in the circle. I had a couple other questions, I thought, as hands went. Yes?
Number 47?
47 on the same set, correct?
Yes.
Okay, so 47. Oh, these are so much fun. Okay, something to do with the quality of this paper or something, the way it does not reflect light or sun. Let's see what we can do. I'm not real pleased with the way that looks. But that is number 47, right?
Yes.
Okay, so I have it up on the screen. And we have 5 times the quantity x plus 3. Then I have a minus 6x. And my argument is that that is supposed to be less than or equal to 3 times the quantity 2x plus 1 and a minus 4x out here. And it's a good thing that didn't get any longer because we're having trouble getting that all on the screen as it is. Now, is there a particular question on it or just how do you do it? What kind of a question am I answering?
I didn't have trouble with any of the rest of them, but for some reason with this one, I did it about 12 times and I came up with a different answer
Each time?
every time, and none of them matched the book.
So you couldn't get 2 out of 3?
No.
Not really. Okay.
No, I just
Let's
was
see what
lost.
happens. 5x plus 15. Now my guess is, if there's an error made, it may be in using the distributive property, but that may not be the case. Minus 6x less than or equal to 6x plus 3 minus 4x. Did we expand okay in the first step? So you got there okay. Interesting. Here's a negative x on the left side plus 15. So what I'm doing at the moment is simplifying each side first, trying to get it a little less messy.
Right?
So I have 2x plus 3. Are we still okay?
Yeah.
You still agree with that?
Yeah. It was the next step, I think,
The
where I
next
got lost.
step. Okay, you have a choice. Now, I'm going to keep my coefficient of x positive. So I'm going to add x to both sides.
Okay.
If I do that, I'll do it in 2 steps here. 15 is less than or equal to 3x plus 3. And what this takes me out of is reversing inequality symbols. That's the only advantage of this. I do need to subtract 3 from both sides, so I'm going to be at 12 less than or equal to 3x. So I'll divide everything by 3 at this point and get 4 less than or equal to x, which is to say that x is greater than or equal to 4.
I'd never added x to both sides, and I think that's where I got confused.
Okay, did you subtract 2x from both sides?
I did.
Okay, we'll
That's what I
subtract 2x from both sides. Alternate form of solution. So you're here, and you're going to subtract 2x from both sides. So as an alternate form for my solution, I'm going to have, where am I going to write that? Let me do it over here. I have a little bit of space. That'll be minus 3x on the left side, correct? And then I'm going to do what? Subtract 15 from both sides. So I'll just do that in one step. And I have negative 12. So I'm going to divide both sides by negative 3. I better do something to indicate that these are not related. So as I do this step, this is where I cautioned you. Write a new line. Because the minute you divide by that negative 3, you have to do what? Reverse the direction of the inequality. Now, I have x. I have a greater than or equal to symbol and a 4, and note the same solution.
I think that's right where I messed up. Was
In
when I
this
was,
step.
Yeah.
The usual error is to come up here and divide by minus 3 and do what? Leave it as a less than or equal, and it doesn't work.
No, it doesn't.
So the best way out of that, given a choice, adjust so that you take the variable to the side that makes it positive. And that's always a choice you have. The wrinkle here that's the downside, you have to be comfortable with this. Saying that 4 is to the left of or equal to x is the same as saying x is to the right of or equal to 4.
Right.
If you can make that switch, then this is a nice technique to use. Other questions? Okay then? Just those 2 questions? Okay, there's one more thing that was asked, and this is email, that I don't have in these particular problems, but I'm going to use the space, Jeff, that I have to the right side of the board here. And what I'm going to do is look at that. If I want to write this, okay, with the, let's see, if we don't have it on the board, but if I want to write it where I have either brackets or parentheses and do it that way, let's look at this solution. This solution, I'm just going to use an arrow up here. How would I write that? Well, on the left side, I want what?
Bracket.
A 4 with a bracket. Now I'm using everything from 4 and what? All the numbers to the
Infinity.
right. So I would want to say comma plus infinity. And what I guess was not quite understood when I've done this earlier, that's not 2 circles together. That's not 2 zeros with a plus sign. That is a new symbol. It's an 8 that looks like it's resting. A sleepy 8. you've seen enough cars called the infinity to understand that there's a symbol that is used for that. Now, what does that symbol mean? Well, it means you keep going to the right forever. All the values from 4, including 4, everything from there on. Now, related to that, let's say that my solution had been something like x less than 2, as an example. How do I write that with the same notation? Parentheses on the right. What do I have on this side now?
Negative.
The negative infinity. So this isn't a negative 0. That's a symbol that means you're taking everything from 2. And note, because I had x less than 2, I do not use the bracket. That's why it's just the parentheses. I'm not using the 2. I'm saying to the left of 2 and going forever to the left. Yes, question. Nicely done, Jeff.
If it was infinity, you don't put a bracket on it?
Correct, because you could never get to infinity or negative infinity. Good question. You just get way out there. I was noticing that Sarah went ahead and got some CDs that were delivered yesterday, and one of the CDs was going back and looking at some of John Denver's work. And the phrase that John Denver used to use was far out. And that, indeed, you're far out on the line when you go to negative infinity and you never get there. You just keep going and going and going. On into the ninth is a phrase that one of my professors used. Or ad nauseum, which is another one I use. It never is achieved. You just get closer and closer. You can. The idea of infinity, no matter how far out you go, there's further you can go. It's a nice phrase poetically. My love for you is infinite, kind of thing that you say to your spouse. And that means no matter how great you think your love is, it is what? It can be more than you ever thought. Of course, somebody has to appreciate mathematics for them to understand the implications of that statement. Any other questions at homework? Yes?
Do you want us to put the positive infinity, or can we just put infinity?
You could put infinity. I would encourage you right now to use the positive symbol with it, because there is a positive and a negative. I'm not going to take credit off for not doing it, but it would be nice to put a plus infinity when you mean you're going to the right. Yes?
I've seen you use a two ways. It's hard for me to draw that. I know why, but is that the same thing as the one that you do like? Is that the same thing? I mean, the sign. I have problems with sides.
Make two circles, have them touch together, and that's close enough for an infinity.
Okay.
It looks like an 8 with
Right.
both loops the same size on the 8. The usual 8 you draw when you write numbers has the top part a little bit smaller than the bottom sometimes. This is like a snowman with
No,
both
but I've
parts
seen you
the
use
same.
that two different. I've seen you do it two different ways.
I've done it 2 different ways.
Yes, you.
It's, you just drew.
Okay.
Did the day.
I'm getting this kind of thing. You did this.
Yeah, and well, you did.
Okay, yeah, I do. Or you can put a 0, 0.
Then the day you did
That's
that.
not the way it usually is done. That was the way it was typed for me in the email, as a 0, 0 with a minus in front of it. I'm assuming that meant minus infinity. Okay, this here could be done by doing the loop-de-loop.
That's what I mean. That's it.
In ice skating, there's what? The figure 8s. We're ice skating a figure 8. And on its side, if you rotate the camera, that's an infinity symbol. Right, just write an 8 and rotate your paper. Or rotate your paper first and write the 8 and then bring it back. Turn your paper vertical or horizontal, write the 8, then when you turn it back, it'll be in the right spot.
I wasn't trying to make a joke out of it, but I seen you do it twice, 2 different ways, and I thought this was something new.
Nope, it's not
Sorry
new.
about that.
No, it was the confusion, though, that came up in the voicemail,
Oh.
or email, I should say, because it was seen as a minus 0. Because I had 2 zeros together, like 0.0. Why would you have a minus sign in front of the 0? Well, I'm not thinking of 0, I'm thinking of infinity. And the negative infinity means you're going to the left forever. That was the point. Or lack of point, because it was not a point. It was going forever. Any other questions? Then fold and pass. Notice that's non-commutative. If you pass and then fold, it won't come out the same.
Well, unless you have a nice person.
Well, if you have somebody at the end of the row who's doing a good job, that's a different story. Okay, we've done one variable. And if I'm talking about one variable, what do you think the next part's going to be? Two variables. And after you talk about two variables, the logical thing would be to talk about three variables or more. One potato, two potato, three potato, four, that kind of thing. So we're into the new chapter. So moving right along, and we find, okay, we'll do this much of the document camp first. Equations in two, fill in the word, variables. Now the question, what have we been using to represent a variable most of the time? X. X, Y, and Z have become the symbols we use to represent variables. So if we have two variables, we're going to do X and Y. If we had three variables, we talk about X, Y, and Z. You know what a box looks like, right? Shoebox. It has a width, a length, and a height, a three-dimensional object. So I could say the formula for volume is LWH. We did that formula just recently. If I don't want to use letters that help me remember what I'm talking about, that's the point of a formula. L stands for length. But if I don't want to worry about that, I could just say X, Y, Z. Volume equals X, Y, Z, where it's understood that X, Y, and Z are the three dimensions. Hence a three-variable problem. A two-variable problem is going to be an equation at this point. Now, we could have inequalities, but we're going to talk for the moment about equations. And I'm going to give you the generic version, generic in the sense that this expression is used to designate a linear equation in two variables. Where have you seen this recently?
We had a problem like that.
We had a problem just like this, and what did I ask you to do in that problem? Still leaving that in the camera. What were you asked to do? Let's see how good your memory is from last week. Okay, we can come off there. They're off the hook at the moment. You were to solve for y, and you obtained an expression, and I gave a name to that new equation where y was on one side. What was it? This is frightening. Why? We've got a test coming up. How many weeks are you going to have to remember on the test?
3.
4.
Oh, 4.
4 weeks. Okay, just keep that in mind. It does pay to go back and review. Okay, what you remembered last week has to be remembered this week. Does the phrase slope, intercept, ring a bell? How could you forget, right? Just wouldn't happen. Slope intercept, I said that was terribly important as you move on because you have to do slope intercept form as you go into courses like the stat course. I'm sure all of you are looking forward to that. Well, maybe not. Okay, this, coming back to the document camp, is a standard form for a linear equation in two variables. If you put it in slope-intercept form, it's going to look different. But this is the way we talk about it as a more or less standard form. Okay? So what the question becomes is one I asked before. Is I'm going to go to the board with no space there. So we're going to go to the side. If we can set the camera up for that. I ask you a question. If I had x plus y equals 11, do you remember that question before? My guess is if you looked at your notes, you might find it. And see, I have proof because the photos are up now. Yesterday, I spent another 4 hours putting photos up for the second week. So all the photos are up for the second week, and I'm still shy of 2 days on the first week. And I'm now behind on the third week. So this is a never-ending process. However, I ask you this question. X plus y equals 11. What numbers work? two numbers that add together to give 11, and let's limit it to the moment to positive integers. 5 and 6, that was my example. What else?
7 and 4.
7 and 4, what else?
9 and 2.
3 and 8, what else?
9 and 2.
2 and 9, what else?
10 and 1.
10 and 1, what else?
11 and 0.
11 and 0, very good. If you go negative integers, what can you use? Negative integers, what can you use for your solution? X plus y is 11. What two numbers? 12 and minus 1. What else?
13 and minus 2.
13 and minus 2. Get the pattern? Okay, now fractions. Give me two mixed numbers that add together to give 11.
22 over 2.
22 over 2 and 0. Well, that reduces to an integer. I want a mixed number. How about 6.5 and 4.5? Right? Fractions are cool. It works. What about square roots? Couldn't do it with square roots. Unless you said the square root of, let's see, what could we do there? Boy, that's a tough one. 6, okay. Square root of 36 and the square root of 25. Yes? The 5 and 6. This is the square root of 36 and the square root of 25. Okay, now we're going to go over to the sideboard. I'm going to just come back to the linear expression here in the document here. And let's see what we can do over here. Jeff, you're remembering all those controls like you never skipped a beat. That's impressive.
Bad memory.
Oh, bad memory. My goodness. If you sat through as much statistics as Jeff has, you probably would have that feeling. X plus y, and this is equal what? 11. Now, I ask you to mentally give me some values. I'm going to make a table. So let's take the same numbers you used. We started with a 5 and a 6, right? And then you said maybe a 3 and an 8. And then you had a 1 and 10. Or you could have said a 10 and a 1. Or you could have said an 8 and a 3. Now, this does become an issue, because I'm going to treat these as pairs. And now, as pairs of numbers, the first part is the x, the second part is the y. And there is a difference between 3-8 and 8-3. Now, the next part, if you've had Math 10, is not new. If you've had Math 20, it is not new. If you're coming out of some distant past, without those two courses, I don't know if you have tried doing the next step. Now, this is intriguing because when I ask a group in statistics who've had 2 semesters of algebra minimally to draw me what I call a coordinate system, they have immediate memory loss. Now, this is going to be called the x, and this is going to be called the y. That's been very traditional, x and y. These are axes. We talk about the x-axis, the y-axis. This place at where they meet is referenced as the origin. Now, some vocabulary time. We are creating a graph. Ends with the letter F in the way it sounds. It's spelled G-R-A-P-H. Graph. There is no T in the sound. What we are going to be doing is referenced as graphene, like caffeine, not graph, which is in some political systems or agricultural work where you try to take a branch from a peach tree and put it onto an apricot tree and call it an apripeach or something. Okay, now, in this case, we are going to graph a point or a pair called an ordered pair, which is also called a point. So the question, where am I going to locate 5, 6? I always, as a reference point, start at the origin and say, I'm going to go left or right first. So the 5 tells me go to the right 5 units. So 1, 2, 3, 4, 5, I go this far to the right. then the 6 tells me to go up. So I'm going to go up 6, and I'm trying to keep this scale somewhat uniform. I'd better do a little better job of it. So I have a 1, 2, 3, 4, 5. That figures I ran out of space. 6 is there. So I'm going to do what now? Go up 6 from this point that I was over 5. Now, technically, you can do this. I do not recommend this. But I'm going to illustrate it because I want you to see something. I'm going to plot the point, P-L-O-T, like a plot of ground. I'm plotting the point. As I graph, bite your lip when you say graph. You won't be tempted to say graph. This is 5, 6, the ordered pair. You plot the point and put the pair with it. Now notice this looks like a rectangle that I've created. So this is sometimes referenced as the rectangular coordinate system. That does suggest there's another kind of system besides the rectangular, and it is referenced as the polar system, which looks like concentric circles. You've seen a bullseye that you try to aim at with an archery set. You try to get the arrow in the center of the circle. You throw darts the same way. Those are concentric circles. So I can tell you how far out in the circles you want to be, and you think of like a clock and the minute hand, and you think in rotating it, so you say how many degrees you want to rotate. That's called a polar system. Right now we're talking about the rectangular. This was originally written about by René Descartes. Now, René Descartes is the same person that you read about in a philosophy course. The Latin form of René Descartes, or Descartes, was Cartesius. So this was the Cartesius system, but that isn't a good adjective form, so it became the Cartesian coordinate system. So you could say rectangular or Cartesian. Now there's a very important point about what I've done here. Let's go back to the idea of a real number line. For every point on the real number line, there is a what? A real number, and vice versa. For every point on this coordinate system, there's an ordered pair, and vice versa. So no matter where I locate a point, and let me do one as reference here, this point right here. Now notice I found the point first, I haven't given you the ordered pair. That's different than what I did before. I had an ordered pair, and then I plotted the point. Can you find me the pair that goes with that point as you look at the TV monitor? Jeff's done a beautiful job of getting that nice and isolated for you in the monitor. What is that ordered pair?
2 and 1.
2, 1. That's about the best you could estimate at the moment, given that that appears to be 1 right there. So you can go back and forth. And if you were doing a Math 10, I would give you problems where you go both ways in this. Now, 2, 1, let's come back. We're going to slide over here or do the camera for my x plus y equals 11. Coming back to that equation, the question I have, does 2 and 1 make this a true statement? If x was 2, y was 1, would that be a true statement?
No.
No. So does 2, 1 as a pair of numbers belong to the solution for that equation? And the answer should be no. Now this table. Are there other solutions besides these numbers? I tried to get you to realize that when we did fractions and we did decimals with square roots. Are there other solutions? Yes. How many solutions are there? Infinitely many. But here's the argument. All the solutions are going to lie on a line I'm going to draw. So now we're going to sketch the graph of the solution set of these or of this equation. So I need to plot another point that is a part of that solution. How about getting something like, let's see what I want here. I'm looking at the space I have as we slide over. This was at 5, right? So if I take that and come out further, see how far I can go before I run out of room. This was at 5, 6, 7, 8, 9, and if I come out here, this would be 10. And I perhaps should not leave the x where I have it. I should move it out here to the end. Now that's not really the end of the axis, because what's true about that axis? It goes forever, and understand x is the horizontal axis. It's like looking at the horizon line, horizontal axis. The vertical, like you're standing up, you're vertical. (10(1) was another solution, right? Ordered pair, 10, 1. So if I plot 10(1), let's see where I go. It's over 10, up 1. Now that's my ordered pair. So I'm going to run out of room here. 10, 1. I'll put the pair to the left. Now both the 10, 1 and the 5, 6 are solutions. What I'm going to now do is join those 2 points with a line. And I'm going to put an arrow on each end of the line. What is that arrow telling you? Now, it's going to go forever, sort of out to infinity on that line, out in the boonies and beyond. Keep going. But every point on that line is a solution. Infinitely many solutions. The technique I'm using here is simply to find 2 points, two pairs of numbers, 2 ordered pairs that make the statement a true statement. Now, in this problem, it was pretty easy because we had x plus y equals 11. But let me change the problem. 2x plus 3y, I want as my new equation. And this time, I'm still going to have the 11 on the right side. So the problem is similar, but a little bit harder. Can you name me a pair of numbers that will work? Eyeballing it. Anybody? X and Y.
4 and 1.
1 and 3.
Okay, first, the 4 and 1. Does that work? 2 times 4 plus 3 times 1. Does that equal 11?
Yeah.
Yes, it does. Okay, what was the other one?
1 and 3.
1 and 3? 2 times 1 plus 3 times 3. Does that work?
Yeah.
Excellent, right? Do you think you'd like to go through life doing this each time? A little bit awkward. Now, what's nice about this, you've given me 2 pairs that involve integers. That's cool. But what happens if you don't want to do it that way? You could say, come back to the equation, and you can say, well, what would happen if x is 5? X is 5. I'm going to let x equal 5. Now, how are you going to find y if x equals 5? Solve, plug and chug, substitute in. You're going to say 2 times 5 plus what? 3 times y is 11. That's 10. Subtract 10 from both sides. So 3y is, and looking at the monitor is going to work better than looking at the board. 3y is?
1.
1. And y is? 1/3. So what is my pair this time?
5 and 1/3.
5, comma, 1/3. Now, which is easier to plot? A 4, 1, or a 5, comma, 1/3?
4, 1.
The 4, 1's a lot easier to plot, right? So when you get pairs of numbers, if you can see, like we did earlier, what works, it sometimes is very nice. If not, you could just do what? Say, choose any x you want and find y. What's a good x to choose?
0.
Right on. 0's the best. Because anything times 0 is? 0. Makes it nice, right? So I'm going to let x equal 0. So come back. That's 2 times 0 plus 3y is equal to 11. So 3y is 11. So y is 11/3. So what's my pair? 0, 11/3. Is that a nice one to plot? Sure. Yeah. Better to do integers than fractions, but it'll work. 11/3 is what? 3 2/3? Estimating where 3 2/3 is a little bit more difficult than estimating where 3 is, but it will work. So now I am going to create a table. Now this time I'm going to put my table horizontal because it doesn't always have to be vertical. And just to understand that there is choice. So the table I'll do with a line up here. And we have an x and a y. And when x was 0, y was what? 11/3. And when x was 5, y was what? 1/3. Now what's the bad thing of doing the table like this?
It looks like a pair.
It doesn't look like it's pair as much, does it? Now if we come back, well we can't, it's way over on the far side. But if we looked, well Jeff's got 2 cameras rotating here. Let's go back to that first table. Now notice doing it that way, your pairs look like pairs. Doing the one we have here, it doesn't look so much like a pair. Do you see the difference? Mm-hmm. But both types of presentations are given in algebra, and one may or may not be preferred. In terms of space, sometimes giving pairs this way, it's easier writing on a page because you don't lose vertical distance. Now let's see what we can do with the plotting. Now this is all approximate, and here's a goal. Be neat, but quick. Quickly neat. I want you to be able to give me a coordinate system with a straight edge, and folks, don't you dare do it freehand.
We have lines on our paper.
Do a straight edge. Okay? Credit cards work. So does a ruler. But somehow or the other, straight edges. But do it quickly. I want you to do it, label it, and do it quickly, and get the practice. Because if you come into a stat course after you've had a 70 from me and you take 10 minutes to draw a coordinate system, you're going to get talked to in real serious ways. Quickly, efficiently, practice it. X, Y, 0. So I need, now let's see, a scale here. I'm going to make my scale fairly large this time because I'm having to estimate what? Things like 1/3, 3 1/3. So the question, I have a 0 and 11/3. So x is 0. Now that means you don't go anywhere, left or right. You just go up, and I'm in trouble. Let's see, I need to get this up higher. I did not plan as well as I thought I should do when I first wrote that. Okay, there's my line segment. We'll let the line going up that high. Now, this is at 1, this is 2, this is 3, this is 4. So 3 2/3. Now, I'm going to go 0, 3 2/3 looks about right there at that point. Now, I'm making my blob pretty large there. you could make them a little bit more tiny on your paper, but make sure it's clear where you're plotting the point. I'm going to not include the ordered pair there because it's what? It's too jumbled, but you should include an ordered pair. Now, the next one is what? Go over 5, and guess what? I'm going to have to extend this out. So I want 5 units now. Let me get an eraser here just briefly. Try cleaning this up, watching the time, so we don't let it get away from us. Here was 1. This is 2. This is 3. There's my space. There's 4. There's 5. I'm just going to put the X out here and get this cleaned up. And now I want what? It was 5 and what? 1/3, which is about there. So this is the ordered pair, 5, 1/3. This was the pair 0, 3 2/3. And what can I now do with just 2 points? Join those two together. The resulting line is the representation of the solution set. Now I'm going to go one step further because we let x be 0, and this up here is called the y-intercept. It's where the line meets the y-axis, hence y-intercept. If I take that same equation, 2x plus 3y is equal to 11, and let y equal 0, what am I going to get? 2x is equal to 11, and x is 11 over 2, so I have the pair 11 halves 0. Note, that is going to be where the line crosses the x-axis. So down here, at this point, we call this the x-intercept. And if you get the x-intercept and the y-intercept, you get 2 points, and it's easy to graph the solution set with 2 points, getting the intercept. So that's a nice way of doing it. X-intercept, y-intercept. Remember when I said slope-intercept? That was the y-intercept we were talking about. So if I solve this for y, and I'm not going to take time to do it, but I'm going to get 11/3 on the right side, and that happens to be where this intercept was, 0, 11/3. It's not coincidental. So I'm going to leave that there. I need to go back to the book so I can give you an idea of what we've covered. This is the whole concept of graphs. There's a lot that I'd like to add to this of practical application. But deciding whether something is a solution or not has been discussed. I would like to bring some language to your attention, looking at the document cam. Notice, this is our grid. This is the coordinate system. You see the origin. And notice the quadrants. 1, 2, 3, 4, counterclockwise.
180.
This is page 180. You see it. You read it. Memorize it. Okay, coming off there. We plotted pairs of numbers, and the process that you're going to do on page 185, 186 is going to continue the work we've done, and I'm going to have you try to do something here with a few problems that are relating to what we do in statistics. Now, the first introductory set of problems is less than I covered today, because what I'd like you to see is what the topic for 3.2 is. And the reason I've done this is we go to the document camp, graphing linear equations in 2 variables. That's what we did today. So I did 3.1 and 3.2 more or less in a combination, and the reason for it, 3.1 should not be new. Let's look at 3.2 again. This is on page 190. The x-intercept, the y-intercept is there. Okay, and that is important. So I'm going to combine 2 sets of problems for homework tonight. So the first part is it's pretty much mundane. It starts on page 183, 184, 185, 186. We're going to go 1 through 70. Okay, now I've got a new expression for you. Let's see if this will work. 3n minus. If I take 3n minus 1, that's not going to do it. Let's try 2x plus 2. Trying to get, that's not going to work. Okay, you know what? 1, 3, 5, 7, 9, those are the odds. Every other odd. 1, 5. So you're going to take and add 4 after you do the first one. So it's 1 plus 4, then add 4 again. You're going to do that up through 70. And you're going to go ahead and look at the material in page 196 and 197. What I want you to try doing for me is 21 through 36 all. So what I'm going to do is on the right side of the board over here, well, I can show you the problem set first. This is the problem set I'm talking about on page 197. So it's 197, 21 through 36 all. 197, 21 through 36 all. And the other page was what?
183.
183, and that was going to be 1 through 70, but it's going to be 1, 5, 9. You get the pattern. Dot, dot, dot. Okay, Jeff, as we close down, dire straits and?
Dire straits and a song called The Bug.
The Bug.
The Bug.
We'll talk more about that tomorrow.